Elevation with impersonation. In the previous section, we discussed how the privileges of an access token decide the access rights of an authenticated user. Now, let's discuss how we can leverage certain privileges for escalation. In the past, security researchers have identified 9 different privileges that may allow for privilege escalation from medium integrity to either high integrity or system integrity, or enable compromise of processes running as another authenticated user. Explaining all 9 privileges in depth and how they may be used to escalate privileges is beyond the scope of this module, but will focus on SE impersonate privilege. This privilege allows us to impersonate any token for which we can get a reference or handle. SE impersonate privilege is quite interesting since the built-in network service account, the local service account, and the default IIS account have it assigned by default. Because of this, gaining code execution on a web server will often give us access to this privilege and potentially offer the possibility to escalate our access. If we have SE impersonate privilege, we can often use the duplicate token EX Win32 API to create a primary token from an impersonation token and create a new process in the context of the impersonated user. When no tokens related to other user accounts are available in memory, we can likely force the system account to give us a token which we can impersonate. To leverage SE impersonate privilege, in this section we're going to use a post-exploitation attack that relies on Windows pipes. Pipes are a means of inter-process communication, just like RPC, COM, or even network sockets. A pipe is a section of shared memory inside the kernel that processes can use for communication. One process, the pipe server, can create a pipe, while other processes, pipe clients, can connect to the pipe and read or write information from or to it, depending on the configured access rights for a given pipe. Anonymous pipes are typically used for communication between parent and child processes, while named pipes are more broadly used. In our examples, we'll make use of named pipes because they have more functionality and, more importantly, they support impersonation. The attack that we're going to simulate, based on a technique developed by security researcher Lee Christensen, can force the system account to connect to a named pipe set up by an attacker. While the technique was originally developed as part of an Active Directory attack, it can also be used locally. It's based on the print spooler service, which is started by default and runs in a system context. We'll discuss the technique in more detail later. For now, it's important to understand that the attack is based on the fact that the print spooler monitors printer object changes and sends change notifications to print clients by connecting to their respective named pipes. If we can create a process running with the SE impersonate privilege that simulates a print client, we will obtain a system token that we can impersonate. To demonstrate this, let's create a C# application that creates a pipe server, waits for a connection, and attempts to impersonate the client that connects to it. The first key component of this attack is the impersonate named pipe client API, which allows impersonation of the token from the account that connects to the pipe if the server has SE impersonate privilege. When impersonate named pipe client is called, the calling thread will use the impersonated token instead of its default token. In order to create our first proof of concept, we'll have to use the create named pipe, connect named pipe, and impersonate named pipe client Win32 APIs. As the name suggests, create named pipe creates a pipe. This API accepts a number of relatively simple arguments. The first, and most important, is the pipe name. All named pipes must have a standardized name format and must be unique on the system. The second argument describes the mode the pipe is opened in. We'll specify a bidirectional pipe with the pipe access duplex enum, using its numerical equivalent of 3. The third argument describes the mode the pipe operates in. We'll specify pipe type byte to directly write and read bytes, along with pipe wait to enable blocking mode. This will allow us to listen on the pipe until it receives a connection. We'll specify the combination of these two modes with the numerical value 0. The maximum number of instances for the pipe is specified through nmax instances. This is primarily used to ensure efficiency in larger applications, and any value between 1 and 255 works for us. N-out buffer size and N-in buffer size define the number of bytes to use for the input and output buffer, respectively. We'll choose one memory page of hex 1000 bytes. The second to last argument defines the default timeout value that is used with the wait named pipe API. Since we're using a blocking named pipe, we don't care about this, and we can choose the default value of 0. For the last argument, we must submit a SID detailing which clients can interact with the pipe. We'll set this to null to allow the system and local administrators to access it. At this point, we'll create a new Visual Studio solution. And insert the pinvoke DLL import statement along with the call to create named pipe. This code expects the pipe name to be passed on the command line. Next, we must invoke connect named pipe. The first argument is a handle to the pipe, which is returned by create named pipe. And the second is a pointer to a structure used in more advanced cases. In our case, we'll simply set this to null. Next, we add the code required to import and call connect named pipe. After we've called connect named pipe, the application will wait for an incoming pipe client. Once a connection is made, we'll call impersonate named pipe client to impersonate the client. Impersonate named pipe client accepts the pipe handle as its only argument per its function prototype. The rather simple code additions importing and calling impersonate named pipe client are added next. At this point, our code will start a pipe server, listen for incoming connections, and impersonate them. If everything works correctly, impersonate named pipe client will assign the impersonated token to the current thread, but we have no way of confirming this in our current application. To verify the success of our attack, we can open the impersonated token with open thread token, and then use get token information to obtain the SID associated with the token. Finally, we can call convert SID to string SID to convert the SID to a readable SID string. While this confirmation does not have to be part of our final exploit, it helps us understand the attack. Let's add these APIs to our code. Let's examine the function prototype for Open Thread Token. According to the function prototype, we must first supply a handle to the thread associated with this token. Since the thread in question is the current thread, we'll use the getCurrentThread Win32 API, which does not require any arguments and simply returns the handle. Next, we must specify the level of access we want to the token. To avoid any issues, we'll ask for all permissions with its numerical value. Open as self specifies whether the API should use the security context of the process or the thread. Since we want to use the impersonated token, we'll set this to false. Finally, we must supply a pointer that will be populated with a handle to the token that is opened. Let's add the required code. Next, we'll invoke getTokenInformation. The API can return a variety of information, but we'll simply request the SID. The first argument is the token we obtained from OpenThreadToken, and the second argument specifies the type of information we want to obtain. Token information class is an enum that contains values specifying the type of information we can retrieve from an access token via getTokenInformation. Since we simply want the SID, we can pass token user, which has the numerical value of 1 for the token information class argument. Token information is a pointer to the output buffer that will be populated by the API, and token information length is the size of the output buffer. Since we don't know the required size of the buffer, the recommended way of using the API is to call it twice. The first time we set these two argument values to null and 0 respectively, and then return length will be populated with the required size. After this, we can allocate an appropriate buffer and call the API a second time. To allocate the token information buffer, we'll use the .NET Marshall alloc h global method, which can allocate unmanaged memory. As the final step, we'll use convert SID to string SID to convert the binary SID to a SID string, which we can read. The first argument is a pointer to the SID. The SID is in the output buffer that was populated by getTokenInformation, but we must extract it first. One way to do this is to define the token user structure, which is part of the token information class used by getTokenInformation, and then marshal a pointer to it with marshal.pointerToStructure. For the last argument, we'll supply the output string. Here we can simply supply an empty pointer, and once it gets populated, marshal it to a C# string with marshal pointer to string auto. Let's add the required structures. Import and code. On the last line of code, we print the SID associated with the token to the console, showing which user we impersonated. Now we have finally written all the code we need to test and better understand the use of named pipes for impersonation and privilege escalation. As previously mentioned, we must execute the code in the context of a user account that has the SE impersonate privilege access right. For our attack demonstration, we'll log into appserve01 as the domain user admin. And use psexec to open a command prompt as the built-in network service account. Before we execute our application, we can verify the user and the presence of SE impersonate privilege in the new command prompt. Now we can transfer it to appserve01. Next, we execute it and supply a random pipe name. To simulate a connection, we can open an elevated command prompt and write to the pipe. When we switch back to the command prompt running our application, we find that a SID has been printed. Our code has impersonated a token and resolved the associated SID. To verify that this SID belongs to the administrator account, we can switch back to the elevated command prompt and dump it. This proves that we have indeed impersonated the built-in domain administrator account. More importantly, we can impersonate anyone who connects to our named pipe. It's now time to test our application leveraging the print spooler service. Communication to the spooler service is done through Print System Remote Protocol, which dates back to 2007 and is not well documented. Fortunately for us, the MSRPRN works through named pipes. The potential for abuse comes from the RPC Open Printer and RPC Remote Find First Printer Change Notification functions. RPC Open Printer allows us to retrieve a handle for the printer server, which is used as an argument to the second API. RPC Remote Find First Printer Change Notification essentially monitors printer object changes and sends change notifications to print clients. Once again, this change notification requires the print spooler to access the print client. If we ensure that the print client is our named pipe, it will obtain a system token that we can impersonate. Sadly, unlike regular Win32 APIs, MSRPRN APIs cannot be called directly. Print spooler functionality resides in an unmanaged library and is called through a proxy function that uses a binary format to pass and invoke underlying functions. The implementation of these calls are beyond the scope of this module. Luckily, we can use the spool sample C# implementation written by Lee Christensen or the PowerShell code written by Vincent Letou. When we use spool sample, we must specify the name of the server to connect to and the name of the server we control, also called the capture server. Since we're performing the attack locally, both servers are the same. This presents a challenge. The print spooler service running as system on the victim needs to contact the simulated print client through our pipe, but since they're on the same host, they in effect require the same pipe name. Because of this, we cannot create the named pipe with the required name. In order to find a solution, we first must understand the problem in detail. To do this, we'll monitor the target system with sysinternal's process monitor, while executing spoolsample.exe against an arbitrary pipe name. First, we'll configure a capture filter with filter, filter, and select process name from the drop-down menu, setting this to spoolserve.exe. We'll then click Add followed by Apply and exit the filter menu by selecting OK. Then we'll execute spool sample and specify the current host name followed by an arbitrary named pipe. Although the application output indicates that a printer notification callback was configured, Process Monitor shows that no access to the arbitrary pipe name has occurred. The reason for this is that before attempting to access the client pipe, the print spooler service validates the pipe path, making sure it matches the default name. Our arbitrary pipe test fails this validation, and consequently, the print spooler service doesn't even attempt to connect to the client. This is why we don't see any connections in Process Monitor. Unfortunately, as mentioned before, we cannot specify spool SS as a name, since it's already in use by the print spooler service we're targeting. At this point, it's useful to know what happens when a file path is supplied to a Win32 API. When directory separators are used as part of the file path, they are converted to canonical form. Specifically, forward slashes will be converted to backward slashes. This is also known as file path normalization. Interestingly enough, a security researcher discovered that if we provide spool sample with an arbitrary pipe name containing a forward slash after the host name, the spooler service will not interpret it correctly, and it will append the default name to our own path before processing it. This effectively bypasses the path validation, and the resulting path is then normalized before the spooler service attempts to send a print object change notification message to the client. This can obviously help us because the pipe name differs from the default name used by the print spooler service, and we can register it to simulate a print client. To verify this, we can repeat our last example, this time supplying an arbitrary pipe name that contains a forward slash in the print client name. We receive an error, and Process Monitor confirms the theory. First, the path we supplied has been switched to a canonical form as part of the full path. Second, spoolserve.exe attempted to access the named pipe. Since we have not created a pipe server by that name, the request failed. At this point, we just need to create a pipe server with that name and simulate a print client. When we execute spool sample, the print spooler service will connect to our pipe. To do this, we'll open another command prompt as network service, because we're demonstrating a scenario where we've exploited a process that has the SE impersonate privilege, and we're trying to escalate to system. And launch our application. Now we'll invoke spool sample to trigger the change notification against the capture server. Our application reveals a connection from the S1518 SID. This SID value belongs to the system account, proving that our technique worked. Excellent. We now have a way of forcing the system account to authenticate to our named pipe, which allows us to impersonate it. To complete this attack, we must now take advantage of the impersonated token, which we will do by first launching a command prompt as system. The Win32 create process with token W API can create a new process based on a token. The token must be a primary token, so we'll first use duplicate token EX to convert the impersonation token to a primary token. First, we'll supply the impersonation token by recovering it with open thread token. We'll request full access to the token with the numerical value hex F01FF for the DW desired access argument. For the third argument, we'll use a default security descriptor for the new token by setting this to null. Impersonation level must be set to security impersonation, which is the access type we currently have to the token. This has a numerical value of 2. For the token type, we'll specify a primary token by setting this to 1. The final argument is a pointer that will be populated with the handle to the duplicated token. With the token duplicated as a primary token, we can call create process with token to create a command prompt as system. First, we'll supply the newly duplicated token, followed by a logon option which we set to its default of 0. For the third and fourth arguments, we'll supply null and the full path of cmd.exe respectively. The creation flags, environment block, and current directory arguments can be set to 0, null, and null, respectively, to select the default options. For the last two arguments, we must pass startup info and process information structures, which are populated by the API during execution. Neither of these are defined in pinvoke imports, so we must define them ourselves, as shown in the following code. With all the code written, we'll compile it and transfer it to the Windows Server 2019 machine. We'll execute this just as before, by first launching our application in the context of the network service to create the pipe server on AppServe01. Next, we'll launch Spool Sample with the capture server set to AppServe01 pipe test, which will force the system account to connect to our named pipe, and a new command prompt is opened. When we interact with it and display the user, we find it to be system. With this attack, we can elevate our privileges from an unprivileged account that has SE impersonate privilege to system on any modern Windows system, including Windows 2019 and the newest versions of Windows 10. Nice. Most native and third-party services that do not require administrative permissions run as network service or local service, partly due to Microsoft's recommendation. This attack technique means that compromising an unprivileged service is just as valuable as a system service. In the next section, we'll demonstrate how to impersonate tokens from other authenticated users, instead of simply advancing straight to system.